Which brings us to the oxygen deficit test. Now, these are considered to be the gold standard tests. These are considered to be the most appropriate, the most valid way of identifying the anaerobic capacity. So all of the issues that we've already encountered in terms of constant load tests, lactate-based tests are going to be discarded. They don't exist within this test. Remember what we've got to do. Remember our benchmarks. It cannot be time limited, right? Because we've got to drain the capacity. It's got to be able to separate aerobic from anaerobic metabolism, fundamentally. And ideally, it should also be able to show the contribution from both the high energy phosphates and glycolysis. So we're going to start with the big one, the one that's perhaps the most widely recognised, which is the maximally accumulated oxygen deficit from MAOD. And in fact, this is from the same paper that we've already referred to within this session. And what MAOD proposed was that the key to understanding this was understanding about what is referred to as the oxygen deficit. And the oxygen deficit is a very, very simple notion. It's a very, very simple idea that exists within exercise science. It's the idea that at the onset of exercise, let's just draw a quick graph here, that if you've got exercise intensity, duration on this axis here, and on this axis here we've got VO2. Okay, so I'm just going to use VO2. As soon as you start to exercise, VO2 does this, and then eventually it should, particularly if we're working kind of submaximally, it should level out. And what they kind of refer to is there's this area here. So I'm just going to put a little line across here, because what they're actually suggesting is at the onset of exercise, as soon as you start exercising, the ATP turnover rate does that. It goes up instantaneously, straight away. That's what's happening at the muscle. But the rate at which you supply the oxygen to the muscle does not go up instantaneously. What we understand is that there is a gradual increase in things like oxygen delivery to the muscle. There's a slow increase in heart rate. Heart rate doesn't suddenly shoot up instantaneously, nor does breathing frequency, nor does the rate at which the oxygen is utilised at the muscle. So until we reach this state here, which is the notion of a steady state condition, this zone here exists. And this zone here, which is the difference between the oxygen which is being consumed, which is my red line, and what should have been consumed had we had an instantaneous increase in oxygen to meet the instantaneous increase in ATP demand, must be coming from anaerobic metabolism. And that is termed the oxygen deficit. So, oops. So with that in mind, MAOD then thought, well, actually, that's very logical. That's clearly a logical argument, because you're borrowing the energy. We know it doesn't increase instantaneously. So he then proposed the nature of what is called the maximally accumulated oxygen deficit. The premise is quite simple. The MAOD is calculated as the difference between the oxygen that would have been consumed and the amount that was actually consumed. So let me explain what we mean by that. So here's a worked up example of this. So I'm just going to see if I can get rid of this. So here's a worked up example. So here we've got, don't worry about panel A for the moment, just focus on panel B. So here we've got an individual that is exercising, and they're exercising beyond VO2 max. This is high intensity exercise, right? It fits. It's high intensity physiology. It's beyond VO2 max. And what MAOD has done is they've made a calculation. Remember, this is really important. VO2 max is maximal oxygen uptake. It sets the limit for the maximum amount of oxygen that we can actually extract from the atmospheric air and use aerobically. You cannot extract any more oxygen. I can work at higher intensities, right? That's what happens when we work anaerobically. But you cannot take in any more oxygen. So VO2 max sets that ceiling. So what they did in this example here is they said, well, there's VO2 max, right? We know what that workload is. So imagine if somebody was able to take in more oxygen. So what they've done is they've made a prediction. And they've said, well, how much oxygen would they theoretically need if they were working at 120% VO2 max? And that's what this line here represents. It's just a theoretical line, right? You can't take that oxygen in. It's not possible, okay? But theoretically, that's what it would look like. So they're using about, what's this? 3,500 mils per minute of oxygen at VO2 max. Theoretically, at 120% VO2 max, they'd be using 5,400 mils per minute of oxygen. They can't do it, but that's theoretically the amount that they would need were they able to sustain 120% VO2 max aerobically. So what they've then done is they've had people exercise at that intensity. So they've worked out that 120% VO2 max, it would give you theoretically this amount of oxygen, but it actually corresponds to, in this case, 350 watts on a bike. And they've just asked the participant to exercise at 350 watts. Now here's the really important thing. As soon as they start to exercise, as we saw on that drawing I just made, as soon as they start to exercise, the ATP turnover rate accelerates instantaneously. So it goes up instantaneously because the demand at the muscle goes up straight away. As soon as you apply the resistance on the bike or the treadmill speed or whatever it is, the muscle needs the ATP. But here's the really cool thing. Remember, and this is really important, that we've been saying all along, that there is no point where you use any energy system independently of another. There's no point where any energy system is turned off. So even if you're working beyond VO2 max, you're going to try and provide energy aerobically. It's never ever going to meet the demand, ever. And so this is what happens. You start using oxygen, and the amount of oxygen, which is accumulated oxygen deficit, rises. But notice, it rises only as high as VO2 max. It can't get any higher. It can't get any higher. So this area under this line represents the accumulated oxygen uptake, the amount of aerobic contribution to this work at 120% VO2 max. The blue area represents the accumulated deficit. That is the difference between the total amount of oxygen had it been possible to work at 120% VO2 max and the amount of oxygen that they were actually able to consume. Therefore, the difference, the blue area between the two, is anaerobic metabolism. Because this is what we were taking in aerobically. This line represents theoretically, if we were able to work aerobically at 120% VO2 max, we're at 120% VO2 max, which is 350 watts. Therefore, this energy has been borrowed, and the only place you can borrow energy from is anaerobic metabolism. Hence the anaerobic or the accumulated deficit. So it comes from a very old philosophy. It comes actually back from some work which was first published in 1924 by Archibald Vivian Hill, when Hill was looking at things like VO2 max, and even work by Krogh, which is slightly earlier than that, I think in kind of the early 20th century. But Medbo really kind of took it to the stage further, which was this notion of estimating what would happen at a fixed workload, 120% VO2 max. So you may be thinking, well, hold on, that's 120% VO2 max. What happened if we went at 130% VO2 max or 110% VO2 max? Well, two things would happen. If we say went at 110% VO2 max, let me see if I can just fiddle around with this to make it kind of work for us. Here we go. So if it was 110% VO2 max, what would happen is this. So 110% VO2 max, instead of having the line at the top of the graph, which is kind of that, what's that, we said about 5,500, 110% VO2 max is probably in the region, let's say it's around about here. Whoops, not drawing it very well. So the actual area would be lower, but because it's a lower intensity, the duration, rather than being 2.5 minutes, might be 3.5 minutes. So the deficit, amazingly, the area should be the same. If it was 130% VO2 max, rather than being at 5,500 mils per minute estimated, it might be at 6,000 mils of oxygen estimated. But the total duration, because the intensity is higher, would be shorter, maybe 1.5 minutes, and therefore the total area would still be the same. So it's a very, very neat kind of idea. Now, in order for us to get this, let me just get my highlighter back. In order for us to get to this, what we have to do is we have to establish the exercise intensity. How do you work out 120% VO2 max? Well, yeah, you could say, well, I just know VO2 max workload, I'll multiply it by 120. It doesn't quite work like that. So what you do is you actually, during either part of the VO2 max test or in a separate trial, you record the oxygen cost at submaximal workloads. This is what these red dots are here. So this is kind of a pre-test. So we actually have to do 2 tests in order to get to the anaerobic capacity with this. We have to measure VO2 max, or estimate VO2 max, and we have to estimate the submaximal cost of exercise at different workloads. And all we do is we interpolate that line. So we're just going to extend that line, so draw basically a line all the way through our data points up to this theoretical 120% VO2 max till it intersects, and then we're going to extrapolate that line back down to the x-axis, and that gives us the relative power output at 120% VO2 max. And in fact, we can work that out with our rearranged equation here. So we just do a y equals mx plus c, and we rearrange it. Rather than knowing y, we want to know x. So it's a very simple rearrangement of the formula. And that gives us the intensity for the trial, and then we just measure oxygen consumption throughout the trial. So how do you select that supramaximal intensity? We're calling it supramaximal because it's beyond VO2 max. Well, it's certainly got to be higher than VO2 max, but it can't be too high. If the intensity becomes too high, I've been referring to the MAOD where they're working 120% VO2 max. If it becomes too high, what actually happens is that the participant becomes fatigued. Either they get kind of neuromuscular fatigue because it's just so fast on a treadmill, they can't maintain the speed, or the intensity is so fast that they just can't sustain it metabolically. So we tend to talk about a window of about 120, 110 maybe, but 120 to 140% VO2 max is kind of an optimal window for these kind of tests. So 110 to 130 as I've got here, 110, 140 you might get away with, as I say. But anywhere within that, remember that if you go for a lower intensity, the estimated cost is lower, but the duration will be longer for the test. It's still going to be blooming hard. So you can just kind of weigh this up in terms of the construction. But there are some kind of recommendations. So the recommendations of the test kind of should fall within a window. Ideally not less than 2 minutes, and probably no greater than 3 minutes. And there's 2 reasons for this. This isn't about time limiting it. So this is still conforming to the green definition. But the reason for this is if it's less than 2 minutes, the rationale is that you probably haven't taxed the anaerobic capacity enough. Think back to the Gaston charts that we showed earlier. Even at 2 minutes, we said there was still a relatively large anaerobic contribution, even if you went for 2.5 minutes. So anything short than that, you've probably not had enough time to really tax the anaerobic capacity. Anything longer than 3 minutes, it's starting to become quite aerobic. It's quite difficult to separate them out. And actually longer than 3 minutes, probably suggests that you're close to VO2 max, which is aerobic, and so you're not generating this kind of big enough deficit to be able to record the anaerobic capacity.